Yes, yes. Okay, Christiansen, one question. Do you want me to tell you when you have 5 minutes left or something? Or do I let
I'm
you?
going to take the time also. You can say it to me, but I have my chronometer here also.
Okay, great.
Thank you, Pedro.
Do you want to start?
Whenever you want.
Okay, so today we have Kristiansen Lara. He's a postdoc at Centro de Estudios Científicos in Chile. He's going to talk about us about stealth constructions and its thermodynamic imprints. Christiansen, take it away.
Thank you very much, Pedro. First of all, I would like to say thanks to the organizers who organized this wonderful and lovely meeting. Thank you very much. Well, as Pedro was saying, the title of this talk is Stealth Construction and its Thermodynamic Imprints. My name is Kristiansen Lara, and this work, which has been done in progress, is done in collaboration with Cristian Erices from Universidad Central and Luis Gajardo from Universidad de Talca. Well, so let me from the very beginning define a stealth. Well, a stealth is a non-trivial scalar field that forgoes the sourcing of the energy momentum tensor. Therefore, it does not gravitate. In this regard, if I will have to summarize my talk in some brief sentences, I would like to say that along this talk, we are going to pursue a novel approach on their construction. And secondly, we are going to explore its thermodynamic consequences. So let me start from scratch in the sense that it is an exciting time to test our ideas in gravitational physics since the prediction and detection of gravitational waves was successfully addressed by LIGO. However, there is an important constraint in GR, which is the no-hair conjecture for black holes. Nonetheless, a way to circumvent the latter is by non-minimally coupling a scalar field such that a scalar hair will emerge, and many scalar solutions exist. But along this talk, we will focus in one of them, which are stealths. So to concretize the discussion, consider a particular gravitational action, your favorite gravitational action, IG, such that the gravitational field G mu is non-minimally coupled to a scalar field phi in the following form. So we have the gravitational action plus the matter one, where the matter is given by this non-minimally coupled through the Ricci tensor scalar field, where chi is the coupling constant different than zero, and U of phi is a self-interacting potential. So the equations of motion are basically, well, when we perform the variation with respect to the geometric action, we obtain the epsilon mu tensor, which in GR can be the Einstein tensor. And with respect to the matter one, we obtain the energy momentum tensor. So basically, the Euler-Lagrange equations of motion are these guys that you can see here. So according to John Wheeler, what does it mean, this equation? Well, it says that space-time tells matter how to move, while the converse is that matter tells space-time how to curve. So a stealth, the definition of a stealth is that epsilon mu is equals to 0 and t mu is equals to 0. These are known as the stealth condition. In other words, the scalar field forgoes the sourcing of the energy momentum tensor, as I was saying from the very beginning. So a prominent example was given in 2+1 dimensions where Eloy Ayonbeato, Cristian Martinez, Jorge Zanelli, they found that for a non-rotating Bethe black hole, GR, non-minimally coupled to a scalar field, admits a stealth overflying this geometry, that this non-trivial configuration for the scalar field, provided the following potential that you can see here, where lambda is given by this expression. So, okay, we have a non-trivial scalar field that forgoes the sourcing of the energy momentum tensor. Another example is in the dimensional Minkowski spacetime. Well, in the same story, GR non-minimally coupled to a scalar field, Ayonbeato, Martinez, Troncoso, and Zanelli, they found a stealth that overflies the Minkowski spacetime with a particular potential. And in this story, there are many other examples that has been reported and worked in different contexts. So the construction obeys the following procedure. So basically, one has to this is step E, is that for a given spacetime ansatz, one solves the set of field equations epsilon mu nu equals to 0. Is the story that one knows, generated from a specific action Ig. So basically, one tries to solve this differential equation and tries to find, for example, the metric function f, if one has a line element with a metric function f, obtaining the corresponding solution G mu. Then step B requires solving the stealth conditions with G mu as a background to obtain a non-trivial scalar field. So these are we dub this procedure as the A to B method, which has been applied in 4, 5, and all of the references that I have here in order to find stealth solutions. No, so in a cartoonish fashion, if you have your favorite gravitational configuration, then step B, after you find it, then you can dress this gravitational configuration with the stealth, with the non-trivial scalar field. So we propose along this talk a reverse approach, B to A. So our starting point is B, which means to satisfy T mu nu first without fixing the background G mu nu to any particular solution, without specifying the form of the gravitational sector, the gravitational action, or equivalently without specific, as I was saying, any purely geometric sector Ig. So basically one aims to find T mu nu equals to 0, the dress, and then you can find your favorite geometry that supports this guy. However, the map is not bijective, and this is a result that we will put in the in our article, is that the mapping is not bijective. Why? Because one can find a different geometry or a different one that supports the same stealth configuration. In this sense, we are now in position to define our general objective, which is to pursue the reverse approach. I call it the reverse approach in the non-minimally coupled case for a simple line element, like the one you are seeing here, where D sigma is a codimension 2 base manifold given by this expression, where omega is given by this quantity here. Is some sense the conformal factor. And here is the Euclidean line element dxi, dxi. They are contracted with some Kronecker deltas. And we are going to explore its consequences. And particularly, we are going to proceed with the reverse approach or B2E method by solving T mu nu first. Then we're going to recover, generalize, and construct new stealth configurations by plugging them in particular gravitational theories and discuss on the thermodynamic signatures that stealths may produce. This is the table of contents, so let me start. So the reverse stealth construction or the B2E method. Well, we focus in the non-minimally coupled scalar field in the dimensions. As I was saying at the very beginning, we will have this matter action where chi different than 0 is the coupling constant and U of phi is a self-interactive potential. We will focus in the following line element, the one that you can see here. Notice that for gamma equals to 0, we have the planar case. For gamma equals to 1, we have the spherical. And for gamma equals to -1, we have the geometry is an hyperboloid. So as I was saying, this sigma denotes the line element of Euclidean codimension 2 base manifold, locally symmetric to the sphere, flat space, or the hyperbolic manifold, where the following constant curvature gamma plus -1 and 0. And here, xi are the Euclidean coordinates of the base manifold. And the Euler-Lagrange equation for the matter action yields the following expression. So our objective is basically solving T mu nu, but equals to 0 in order that we forego its sourcing. So its off-diagonal components reads like this. However, notice that the above can be rewritten in a Peeling form according to the following change of variables like this. So where phi, as I was saying, is the scalar field, and just for saying some notation, psi will be defined as the auxiliary scalar field, just that. And with this redefinition, we find that the off-diagonal components of the energy momentum tensor reads like this. And this can be solved by hand in a paper sheet, and the latter allow us to find the following expression immediately, where T, R, and Xi are functions that depends only on T, R, and the base manifold or transverse coordinates Xi respectively. So using this expression, the next step is to determine the form of the unknown functions t, r, and xi. So taking the difference between the transverse sector for fixed but distinct spatial coordinates, we arrive to the following differential equation that is really solved to this expression that you can see here, where A, B, and C are integration constants. So at the moment, we have that all the energy momentum tensor is diagonal, and also its transverse components are equal. Regarding the difference between the temporal one and the radial one, we arrive to this differential equation where here primes stands for radial and dots for temporal derivatives respectively. So let me study briefly this equation. So to this equation, we are going to apply these derivatives operators. And notice that when we apply these derivatives, the only term that is going to survive, it will be the one given by this expression that you can see here. So, okay, we apply the derivatives on the red one, and we obtain this guy. So this guy is saying to us, okay, look, we will have two branches. The first one is a time-dependent configuration like this. And notice the following, that for here, you have to solve an equation. Okay, you have to say or t dot is equals to 0 or f3 prime is equals to 0. So in this case, if f3 prime is equals to 0, we will not fix the time dependency of the scalar field. However, you will have to find the metric function without specifying at this moment the gravitational sector. So the metric function was determined at this point. While on the other hand, we have another branch, which is for the time-independent configuration. If you vanish this guy here, you will find that, okay, the metric function is not completely specified and this guy vanished. So basically you have this branch. And along this talk, we will focus on this branch. And that's it. So the metric function is not completely specified. And this, we will find how we are going to find the metric function, well, by solving the difference between the temporal and the transverse sector. And it will be given by this expression where chi, capital Chi, 2, 1, and 0 is a differential equation for the metric function f. Okay, so we have to solve this. So we will consider a branch here, which is a spatial coordinate dependent. So notice that here I have this lowercase b. Lowercase b was belonging to this function here that belongs here, if you got lost. So if b is different than 0, okay, I will have to solve chi1 equals to 0, which allow us to find the following metric function. And let me emphasize this result. Why? Because this metric function is saying to us that without specifying any gravitational theory, the stealth provides a metric function that tells us to go beyond ngr. Why of this novel decaying term? So now replacing the metric function in chi0 and chi2, the following conditions are obtained. Okay, these notice that where a, c, I are integration constants, and from the first equation, we can isolate R1 and rewrite it in terms of gamma, Ci, and A, and replace it here. And we will arrive to the following stealth configuration. So basically, we have this guy, and now we have to solve the second one, the one here in blue. So notice that in order to solve it, okay, one has to say the following: if R0 is different than 0, or R0 is equal to 0. So notice that for R0 is equal to 0, we return to this expression that you can see here, because it's saying nothing about the metric function. However, if R0 is different than 0, we will have to impose conditions on B on chi. So is B is equal to 0 or chi is equal to this guy. The two options converge to the same expression, because notice that if b is equal to 0, this guy vanishes. So basically, you will have this metric function, which is nothing that de Sitter, or Minkowski in d dimensions. So what I am saying here is that I am providing, in quotes, in comillas, I don't know how to say that in English, but I am saying that anti-de Sitter, Minkowski, and de Sitter, they will always have a stealth. In some sense, it is a yes-go condition. So this finished the first part. Regarding the second one, we are going to see how this procedure can be embedded by specifying gravitational sectors in concretely. And also, for the sake of the time, I didn't talk about the time-dependent configuration and the other ones, just for the sake of time.
Yes, I was about to say 5 minutes.
So we recover several results from the literature along this. So our article, we recover all of these results from the literature, and also we generalize it, many of them. Nonetheless, I am not going to explain it, but we recovered it from GR, new massive gravity, Lovelock, Gauss-Bonnet, conformal gravity. Okay, but for the sake of the time, let me emphasize our result regarding this example. So this is the stealth of Bravo-Gaete and Hassane of 2013. So the equations of motion are given by this expression that you may read here, where epsilon of phi is the following equation, the Klein-Gordon equation, where K mu is the Gauss-Bonnet tensor. Okay, but this is just technicalities. So basically, we have to solve this equation, the stealth condition. So the authors, Bravo, Gaete, and Hassane, they found the following stealth configuration, this metric function with this scalar field with this potential. And we are going to recover it from our construction. It will be very easy. Remember this slide, please. So with this slide in mind, remember this metric function that we have here and this scalar field. So I'm going to put it anyway. So the metric function was this guy, the scalar field was this guy, and the conformal factor this guy. So for omega, for gamma equals to 0, omega goes to 1. Why? Because this guy vanishes, so we have omega equals to 1. Good. So the scalar field reads like this, and the metric function like that. Now, with chi equals to 1 over 6 and R0 equals to Ci equals to Bi equals to 0 in 5 dimensions, the scalar field reduces to this expression. Okay, so this expression is equivalent to this, and this is equivalent to this. So 1 over third divided 1 over third is just 1, like this. Perfect. Now, on the other hand, for the metric function, well, we replace. Basically, for the metric function, we replace the dimension chi. We have this expression, which reduces to this one, which reduces to this one, and 2 minus 2 is 0. So basically, we have this, which is in agreement with the result of this by recognizing B as minus M. So we recover this configuration. So this was the applying procedure. Of course, with the same method, we can recover all of these results. Now, regarding the thermodynamic imprints, well, this is a more elucubrative one, but let me say some things. I am finishing. Well, because epsilon mu nu is equals to 0, are stealth configurations detectable? We know these guys, they do not gravitate. They don't appear in the equations of motion. So what they are? What are the imprints if they have? Well, due to its particular nature, it only has been shown that they change the Euclidean action, leaving the discussion on its thermodynamic properties to be addressed elsewhere. So we provide a short glimpse on this discussion. So we consider the same example as before in 5 dimensions for the Bravo-Gaete-Hassane stealth configuration. And the equations of motion were like this. And the authors found the following configuration that I showed you before. So now let me redefine R1 as 1 over capital phi. So we have basically this configuration. So we use the reduced Hamiltonian approach for the non-minimally coupled scalar field. So the Euclidean action reads like this. where B is a boundary term introduced in the action. We know that this boundary term has to ensure that the action is differential, and one can arrive to the equations of motion. It's an old story. So for the following asymptotic variations like this, the boundary term is expressed like this, where capital theta is this expression. So notice the following, that with this expression, it is possible with sigma, the volume element of the base manifold, A plus the area of the horizon, gamma equals to 0, it is possible to find that the mass and the entropy are shifted by the action of the stealth. The stealth configuration shift the mass and shift the entropy in a particular form according to this capital theta expression given by this integral, which is non-trivial. This integral is very non-trivial. So replacing the stealth configuration and you are done. What I am saying with this, replace these guys here and you are done. You will prove that the stealth produces a shift on the mass and the entropy. And this shift has to have must satisfy some criteria. It has to be non-zero, non-trivial, and non-divergent. So this suggests that there will exist some classification of stealths. We are writing about that. So in conclusion, we have solved T mu for different branches. For spatial coordinate dependence, be different than 0. The rest branches need analog details. The reverse approach is strong enough to fix the metric function. The metric function without specifying the gravitational sector, and finding black hole stealths like this requires to go beyond GR. Any gravitational, also, it is important to emphasize that any gravitational theory that admits this metric function as a solution in d greater than 3 dimensions, I would like to say that the aforementioned procedure was taken for d greater than 4 dimensions, but the same procedure can be done for 3 dimensions, and it will support a stealth. So basically, as I was saying, anti-de Sitter, de Sitter, or Minkowski in dimensions greater than 3, they will support a stealth. And finally, it seems that there are two types of stealths, healthy versus non-healthy. They must render a non-vanishing, non-trivial, and non-divergent shift to the mass and the entropy. So this was my talk. Thank you very much.
Thank you, Kristiansen, very much. I have a couple of questions, but let me say that we have a couple of minutes for questions. So if anyone wants to shoot, it is time. Mati.
Kristiansen, very nice talk. I have a question related to the fact that you have a T mu that is 0, so the trace is 0. So maybe you have a trace anomaly somewhere if you do the quantum level. Is this correct? Because this is all classical.
I don't know, because my analysis, I'm going to say the honest answer is that I don't know. now arguing in this sense, I don't know. But it's an interesting question. Yeah, I didn't think about that, to be honest. But I don't know. I don't know, to be honest.
You can, if you do the 2-point function, 3-point function of this, maybe it's not doable, but if you try to do it, what will be the free theory that you use? Is because you left the zeta that is like the mass, like arbitrary, right? But
sorry, what?
If you do the 2-point function, 3-point function, what do you get with this?
Okay.
Yeah, what do you get with this? Can you measure this or?
That's a very interesting question. We are discussing on that because we're trying to find a method, a mechanism to detect stealth. So we found that they shift the mass and the entropy, but we don't know if this shift. So for example, think if you have a celestial object, and this celestial object, you measure its mass, for example, and its mass gives you 8, for example, number 8.
Yeah.
You don't know if this number 8 received a contribution for this from this stealth configuration or not.
Yeah.
So exactly. So we don't know yet if this guy is detectable or not. So that's the only thing I can answer right now, because we are working on that, and we are trying to seek if this guy, okay, this guy alters the charges, okay, but we don't know if it's detectable at the end of the day. We don't know it yet.
Okay. So additionally, there is a thing that these fields seems like go to the power of zeta, right? And there are
Powers of
particular
chi,
values
yes.
of
Powers
yeah,
of chi, yes.
and there are particular values of chi that are half integers or something like that. You get the square roots, so maybe you get branch cut or something like that around,
No, for example, if you
or
look this
maybe it's all
table.
positive in the
No,
interval.
because solving to mu equals to 0 was completely done in general for every chi, different than chi equals to 1/4. But 1/4 is a particular case that we also addressed. Nonetheless, please look this table. So in this table, when you have to specify your gravitational theory,
Yeah.
then you will have to specify a particular form of this coupling constant chi. So for pneumatic gravity,
Okay.
for example, chi will be 1/8. So for Gauss-Bonnet, chi is going to be 1/6. For Lovelock, this guy, and for conformal gravity, this guy, while in GR is arbitrary. But if you specify the gravitational sector and you glue all results that you have by solving T mu equals to 0, and then you compare it with your solution in the vacuum, you have to match, you must match the coefficients of the metric functions, and you're done. Then you will show that that configuration will admit a stealth.
But
So the
yeah.
so yes, please.
No, no, but this
Our
coupling.
clocks are on fire, Mati. So maybe if you can ask a yes
Okay.
no question, or maybe
Yeah, yeah, yes or no
let someone
question.
else. Okay.
But this guy
Please, please.
should be bounded, right? Because if you turn off the potential, you should get the free theory, and you have this theory should be unitary or something like that. I mean, so you
Sure, but,
can.
but remember but remember that the potential was always powers of chi.
Ah,
And
okay,
remember that its constants also depend on chi. So I think everything is okay.
okay. Thank you.
Thank you, Matthias.
Okay, please, quick questions at Arpan.
I have a couple of questions. So one thing is that so the stealth field that you are talking about. So here you are introducing the stealth field as some effective theory, or the stealth fields come from some more fundamental theory. This is one question, and another question is regarding this yes go theorem. So are you saying
I
that
didn't say theorem. I say yes, go condition.
yes, yes go condition, sorry.
Yes.
So that yes go condition, does it mean that whenever this FR has that profile, I get ADS, DS and flat as the solution? Is it the
I
statement?
will I will I will answer your last question immediately. Any gravitational theory that admits anti-de Sitter, de Sitter or Minkowski will, if it's not minimally coupled to a scalar field, then it will support a stealth configuration.
Okay, okay. So
Regarding the first one, from the phenomenological or theoretical point of view, okay, here I am doing it from the theoretical point of view. Nonetheless, Eloy Ayon Beato has explored the consequences of stealth configurations in cosmological backgrounds. For example, in Friedman, Lemaitre, Robertson, Walker.
no, no. I mean, my question was basically whether this still configuration, I mean, can be derived from some more fundamental theories. I mean, you are introducing a scalar field, so those kind of things can come from something more fundamental.
Ah, ooh, I don't know, to be honest. I don't know. It's an interesting question, but no, but it's like in field theory. It's like, okay, if you have a massive action coupled to your favorite theory, the field theory, I would like to ask the same question that you did. It's like, okay, we can deduce this from a more fundamental theory. I don't know. It's like if you have decline Gordon field non-minimally coupled to another thing. I don't know if this will be uh, given by a more fundamental one. I don't know how to answer your question, but it's interesting.
Thank you, and also thank you. Like your slides are very beautiful.
Thanks.
Okay, Marcelo, please.
Sí, really good, really quick question. Buena, Kristiansen, very good talk. My
Thanks.
question is related to this correction to the mass and the entropy. This capital theta, is this a number or it depends on some integration constant that appear in your scalar?
Very good question. Very good. It depends on integration constants of the stealth, whose variation is different than zero. That's why I said that the shift is different than zero, non-trivial and non-divergent.
Okay, and okay, very good, super interesting. Thank
Thanks.
you. Because maybe the entropy can have, if you count in some way the microstate, have to you need to take account this theta that appear in this.
I understand.
So very interesting. Thank you very much.
No, but that's the reason. Sorry, that's the reason I was saying that the shift has to fulfill these three criteria.
Okay, so I have questions regarding that shift in the entropy too, but
sorry,
I will.
Robinson was asking before he was trying to ask a lot of time ago, I think.
Okay. Robinson, you have a question?
Yeah, I am a little confused because if I try to do this for supergravity, where we have like near streamal black holes, and supposedly there is this attractor mechanism that said that the charges can depend only in the scalar field at the horizon, but not at infinity. But your result is telling us that the charges are depending of the scalar field at infinity. So it looks like a little contradictory. Or
No,
maybe
it depends. It depends on the integration constants of the scalar field. And this can happen not only on stealths. It's like for example, in the article of Troncoso, Staforelli, or Sanelli and Martinez, they present, okay, black holes non-minimally coupled to scalar fields that are not stealths. Okay, they have their mass and their entropy, so everything is okay. So, okay, this is a matter field that you are non-minimally coupling to GR. That's my answer, but regarding to supergravity, no, you kill me. I know nothing about that.
maybe
Sorry.
it's not consistent with like the supersymmetric condition and all of that.
I see. Okay. I don't know, to be honest.
Okay, well, we thank Kristiansen again. I will ask my questions in an email probably. Thanks, Kristiansen. Very nice talk. Alejandro, are you there?
Yes.